So in this video, we're going to use some properties of logs and also look at some functions that involve exponents. So these properties of logs are going to help us to solve, because in this case, we're going to be solving for an exponent. So this is continuous exponential growth models. We talked about exponential growth as being y equals a times 1 plus r to the t power. And we also saw an example in a previous video where we had money that was compounded annually. That meant it was applied once. Well, money can also, you can apply that compounding continuously, like where it's always being applied. So that's what we're going to look at here, the continuous exponential growth model. So if it's compounded continually, or in this case, we see that we have a number of bacteria in a certain population increases according to a continuous exponential growth model. And we start with a sample of 4,000 bacteria that reached the size of 4,400 in 2.5 hours. Find the growth rate parameter. All right, so what we're going to do is this is the formula for exponential, continuous exponential growth. So again, we saw that exponential growth, this is continuous. And we see this e value again. So this is where this comes in, this e that I mentioned is kind of like that same idea as pi, and it comes in with exponential growth where it's continuous. All right, so first thing to note is that a is representing the amount, the total value, just like the y did in exponential growth. P is principal or the initial. This works for money as well. So if it's compounding continually, you invest money and it's compounding continually, you would use this formula. R is the rate and t is the time. Now again, e looks like it's a variable, but it's actually a number. So if you plug that into your calculator, you'll see that it is actually a number, just like pi is a number. All right, so what I want to figure out in this sample, or in this example, is I want to figure out exactly what's going in for what. So a sample of 4,000, this is what I started with. So this is going to be my p-value. Reach the size, the final value is 4,400. So this is going to be your a. In 2.5 hours, that's time, t. The thing that I do not know is the rate. So that will be the unknown, r. So I'm going to go ahead and plug this into the formula. I'm going to rewrite it first. So 4,400 equals 4,000 e to the 2.5 r. So t is the 2.5. I don't know what r is, so I'm plugging that in just as r. And that's what I'm going to be solving for. Now, just like in previous problems, you have this 4,000 times here. The inverse of multiplication is division. So I'm going to go ahead and take care of that. Divide by the 4,000 on both sides. And I will get 1.1 here equals e to the 2.5 r. All right, we have not learned anything up to this point, or seen anything rather, I should say, that would allow us to solve this. You have not seen any examples where you can solve an exponent, but I mentioned in the previous video where we were talking about properties of exponents, properties of logarithms that will allow us to solve for this. And that is that, remember that ln e is 1. So if you take the natural log of e, it's just equal to 1. So they are inverse operations of each other. So we can actually get rid of this e by taking ln of that e. So I'm going to do that on both sides here. So I can manage it with my marker. All right, so I'm going to take ln of 1.1 equals ln of e to the 2.5r. Remember, if you do something on one side of an equation, you have to do it to the other side. So I'm going to take the ln because I know that I can get rid of that, and I'm going to be able to use a property along the way. So I'm going to leave this as ln 1.1. And then over here, I'm going to use that property where I can pull this down, and it's going to be 2.5r times ln e. But remember, ln e is 1, so that can go away. And this is just going to be ln 1.1 equals 2.5r. And now this is a simple problem that I can solve. It's a linear equation. I can just divide by 2.5 on both sides. And if you type that in your calculator, ln of 1.1, there is an ln function on your calculator, divided by 2.5, you will get r equals 0.038. Now here's the nice thing, in these problems, your rate remember it's a percentage. So if you end up with something crazy like 500 for your R value, that doesn't make any sense. So you can kind of look to see if this makes sense. This as a percent, if we move that over 2 units, is 3.8%, and that does make sense in this context. In 2.5 hours, it increased from 4,000 to 4,400. It's increasing pretty rapidly. That's a pretty good rate of increase. And so that does make sense in the context of the problem, especially with money too. You know, if you're talking about interest rates, like you're not going to see an interest rate of 80%. That's just, you know, that's just unheard of. You wouldn't see that. Interest rates are usually going to be like, it could be 0.5% all the way up to maybe 8%. But you're not going to see anything outside of that range. So keep that in mind when you're solving problems. Always, especially, you know, with word problems, always just make sure that your final answer makes sense in the context of the problem. But here you can see where we use that, and this is where logarithms really come in handy, is to solve these exponential equations where the unknown is in the exponent, because we can use those properties to bring that exponent down, and then again that natural log of e is 1. All right, so this will work with those money problems too. Just pay attention to the wording, whether with the money, if it says that it's compounding annually, then you would use the other formula. If it says it's compounding continuously, then you will use this formula. All right.